Okay, we're going to continue to talk about about these operator equations. So again, we want to ask the question, how do we solve operator equations that are of the form ax equals to y, where we're given y, we have knowledge of the operator a, and we're trying to solve x. Again, remember that a maps h1 to h2, it's bounded. H1 and H2 are Hilbert spaces, and then the range space of A is closed. So these range space of A being closed is something that will be true for almost all regular operators that we encounter. Okay, so we have this picture that I showed before, and this picture actually, from this picture, we can see a number of different facts. So let me try to argue through why these facts are true. So yeah, we've established, by the way, everything on this picture, right? This should be the general operator equation. That H2 is the orthogonal decomposition of the range space of A, and the null space of A star. H1 in general is the orthogonal decomposition of the range space of A star and the null space of A, and then the dimensions are the same. Sorry, I've got the wrong figure here. Okay, so fact one, ax equals y has a solution if and only if y is in the range space of A. Okay, so in other words, if we were to have a y that's over here that includes something that's in the null space of A, well, we can't get to that. We can't get to, there's no x that will get to that y, right? So the only way this is true is if this y is in fact in the range space of A. This is important for things like, for example, least squares problems, where we'll be solving things where in general the right-hand side y has an element that's in the null space and an element that's in the range space, so that it will have no solution. So the only way we have a solution to this operator equation is if if we can show that it's in fact in the range space of A. Now, another way we could say that is that ax equals y has a solution if only if y is orthogonal to the null space of A star. In other words, since y has to be in the range space of A, that means that y has to be orthogonal to the null space of A star. Okay, so those are just restatements of the same statement, and it becomes clear in a picture like this. Okay, a couple other facts that we can say. So ax equals b has a solution. If it has a solution, then it's a unique solution if and only if the null space of A is equal to 0. Okay, so again, we have some element over here in y, and if it in fact comes from something, it comes from something that contains elements in the null space and the range null space of A and the range space of A hat, we'll never be able to get back to the element that's in the null space of A, because it gets completely zeroed out, right? Because we have A xr plus xn, where this is in the range space of A star, this is the range space of A, and that's just A xr equal to y. And so, we say it's unique. Okay, sorry. So, in other words, yeah, actually, if something is so in other words, if you have a solution, let's suppose it has a solution, then we can, in fact, add to that solution. If the null space is not unique, we can add to that solution. So you take any solution, it doesn't necessarily have to be, so it has a solution, let's say ax hat equal to y. I can add to that anything that's in the null space, ax hat plus xn, you see. And that's going to be, since that's ax hat plus axn, and xn is in the null space, this is just ax hat equal to y. And so x hat plus xn is also a solution. And since it's a space, we can multiply by any scalar In other words, anything that's in the span of the basis vectors will also be the basis vectors of the null space of A. We can add that to our current solution. We get another solution. And since there's an infinite number of elements in our field, there'll be an infinite number of solutions. Yeah. So in fact, you have an infinite number of solutions. And that's the statement down here, that if the null space is not 0 and y is in the range space of A, then ax equal y has an infinite number of solutions. So really, fact 3 and 4 are essentially the same thing. If it has a solution, then it's unique if and only if the null space of A is equal to 0. And if it's not equal, the null space of A is not equal to 0, then it has an infinite number of solutions. All right. And then our last statement, A inverse exists, implies that the null space of A is equal to 0. Because, well, if there's an infinite number of solutions to ax equals to y, the only way to go start y, take y and do an inverse is to go back to one solution. So the only way, you can have an inverse is if it's a one-to-one mapping. And it's only a one-to-one mapping when the null space of A is equal to 0. So A star inverse exists only when the null space of A is exactly equal to 0. In other words, there's nothing on this side. So we would have our telephone pole diagram would have to look like, this, where A star maps just to the range space of A star, and there's no null space. The null space of A is equal to 0. Okay, so now let's talk about matrices in particular, and we'll talk about the rank of a matrix. All right, so if we have a matrix A that's in complex M by N space, we say the row rank of A is the number of linearly independent rows. So in other words, the way we could write this is A is going to be, for example, A1H down to AMH, and each of this set, A1 up to AM, this set has to be, the number of linearly independent elements inside this set is the row rank of A. Similarly, we can define the column rank of A to be the number of linearly independent columns. Okay, now let's think about the range space of A. Okay, so if I have let's suppose with column rank I have A is equal to like B1 up to Bn. So these are the columns, and this column rank is how many of these guys are linearly independent. Okay, now if I look at A times X, it's going to be B1, B2 up to Bn times X1, X2 down to Xn, and that's going to be the sum, X1, B1 plus Xn, Bn. So that implies that this element is in the span of these of the columns, right? It's in the span of the columns of A. And we know that this element is also, this is also in the range space of A. So this has to be equal to the range space of A. In fact, the range space of A is exactly equal to the span of the column vectors. And you could do a similar thing with AH. Of course, AHY is going to be A1 up to AM, Y1 down to YM. And of course, this guy is going to be in the span of A1 up to AM, and it's also in in the range space of AH. And so the span of the rows is going to be equal to the range space of A. So since the range space of A is equal to the span of the columns of A, then it's true that the dimension of the range space of A is exactly equal to the column rank. And since the range space of AH is the span of the rows of A, we know that the dimension of the range space of AH is equal to the row rank. And since we just showed that the dimension of the range space of A is equal to the dimension of the range space of A star, we have to have that the column rank is equal to the row rank. Or in other words, another way of saying this is that the rank of A is equal to the rank of A. Oh, well, maybe, okay, let me say something about that here in just a minute. So the row rank has to equal the column rank. So for a matrix, it doesn't really make sense to define both the column rank and the row rank since they're always the same. So we have another definition. The rank of A is the number of linearly independent rows or columns. So we had this, since the dimension is equal to the same, we have that the rank of A is then equal to the rank of AH. And we say that a matrix A is full rank if the rank of the matrix is the minimum of n by m. So for example, if we have A is equal to 1, 2, 3, 4, and let's say 0, 5, 6, 7, well, the number of linearly independent rows, these two rows are going to be linearly independent, since the only way to sum those together and get 0 is if the coefficient that multiplies this guy is 0, right? Or those two elements don't go to 0. And if it's 0, then we have to have C1 is equal to 0. So this would be, the row rank would be 2. And actually we can look at the column rank. There's only 2 columns. So the column rank, in fact, C1 times this column plus C2 times that column equal to 0. Because of the first element, the first C1 has to be equal to 0. And that would, since these others are non-zero, that means the second one would have to be equal to 0. So these have 2 linearly independent columns. And we can conclude from that there's only two linearly independent rows. There's no other rows that would be linearly independent. So the rank of A here, in fact, the rank of A is equal to 2, and that's equal to the minimum of, n is 2 and m is 4. So this is full rank. Okay, so matrix is full rank. It doesn't have to be square, but if it's full rank, then the rank is equal to the minimum of m and n, which means there's no superfluous columns or rows, essentially. Okay, we have famous inequality called Sylvester's inequality. I'm not going to prove this, but we use this result quite often when we're talking about ranks of matrices. So if I have 2 matrices, A and B, and the inner dimension here has to be compatible. So A is Q by N, B is N by P, so the inner dimension is N, okay? And so we can multiply these two together. Again, the inner dimension here is N. So the rank of, when we multiply 2 matrices together, suppose we know the rank of A and the rank of B, what's the rank of A times B? Okay, when we multiply these 2 matrices together, that's going to be less than or equal to the minimum of the rank of A and the rank of B, and greater than or equal to the rank of A plus the rank of B minus the inner dimension. So here's an important application. We have, a 2 column vectors. X is in Rm, Y is in Rn. So for example, let's say X is equal to, 1, to 3. Y is equal to, I don't know, 4, 5. Okay, then X, Y transpose. This is 3 by 1, and this is 2 by 1. X is going to be 3 by 1, and Y transpose is 1 by 2. So this is going to be 1, 2, 3 times 4, 5. And when we multiply these out, we take the first row times the first column. That's just going to be 4. First row times the second column, that's 5. Second row times the first column, that'll be 8. Then 10, 12, 15. Okay, now this guy, that's equal to XY transpose. Okay, so let's go through Sylvester's inequality. So the rank of XY transpose has to be less than or equal to the minimum of the rank of X, rank of Y, and greater than or equal to the rank of X plus the rank of Y minus the inner dimension, which is 1, right? Because we have a 3 by 1 and a 1 by 2, so the inner dimension here is 1. Okay, so what is the rank of X? X is now a single column, and so it has to be rank 1. Again, it's going to be, how many linearly independent vectors are there in X? I guess, there's only 1. And how many linearly independent vectors are there in Y? There's only 1. And so this guy is equal to 1. Rank of Y is equal to 1. So the minimum is equal to 1. Rank of X is equal to 1. Rank of Y is equal to 1. So this is 1. So the rank of XY transpose has to be equal to 1. Okay. So if we take two row vectors, this is called the outer product, not the inner product. The inner product of two row vectors, of course, is a scalar. The outer product of two row vectors is going to be a matrix. And that matrix, whenever the matrix of an outer product is going to be rank 1. Okay, so that's the end of this little segment.